Previously, we've seen that we could use integration to find the area under a single curve. Now we're going to take a look at how we might use similar techniques to find the area between two curves. We can calculate the area under a single curve by approximating that area with a series of rectangles. We divide the region up into n distinct subregions, drawing a rectangle with a height given by the function for each of those regions, and then calculate the area of each of those rectangles. Adding them up gives us an approximation of the area under that curve. By creating more and more rectangles, letting the number of rectangles go to infinity, which then results in each of their widths getting smaller and smaller, we get a closer and closer approximation to the area under that curve. Taking the limit as n goes to infinity, where n is the number of rectangles, gives us the integral over that region, which is exactly equal to the area under that curve. We can use a similar process to find the area between two curves. Imagine dividing that area up into a series of rectangles. Then we know that that area is approximately equal to the sum from I equals 1 to n of h sub x sub I times delta x, where h of x sub I represents the height of the ith rectangle, and delta x represents the width of each of those rectangles. Now, if we let the number of rectangles increase, effectively letting n go to infinity, we see that the exact area is going to be the limit as n goes to infinity of that sum. That limit is exactly the integral from a to b of h of x dx, where h of x is a function that represents the height of any given rectangle. If g of x represents the upper function in our graph and f of x represents the lower function, then we can see that the height of each rectangle is going to be given by g of x minus f of x. We can conclude then that our area must be exactly equal to the integral from a to b of g of x, our upper function, minus f of x, our lower function, dx, where a and b define the interval that we are looking to find the area over. Summing all of that up, if g of x is our upper function and f of x is our lower function, and a and b are endpoints that define that interval, we know that the area of the region between g of x and f of x is given by the integral from a to b of g of x minus f of x dx. Let's try an example. In this graph, we see that g of x is the line x plus 1, and f of x is the parabola x minus 2 squared plus 1. We can see that these two graphs intersect each other at x equals 1 and x equals 4, so those are the values that outline our region. Our area then, we know, is given by the integral from a to b of h of x dx, where h is the height. So we get the integral from 1 to 4 of g of x minus f of x dx, which then becomes the integral from 1 to 4 of the function x plus 1 minus the function x minus 2 squared plus 1 dx. Simplifying this integral, we get the integral from 1 to 4 of x plus 1 minus x squared minus 4x plus 5 dx. Combining those, we get the integral from 1 to 4 of negative x squared plus 5x minus 4 dx. Taking antiderivatives, we see that that is negative 1/3 x to the third plus 5/2 x squared minus 4x integrated from 1 to 4, giving us, plugging in 4, we get negative 64/3 plus 5/2 times 16 minus 4 times 4. Subtracting what we get when we plug in 1, we get minus negative 1/3 plus 5/2 minus 4. Combining our like terms, we have negative 63/3, 75/2, and negative 12, which all combines to give us negative 21 plus 37.5 minus 12 for a total area of 4.5 units squared. Sometimes drawing in vertical slices or rectangles won't work. In the graph here, we can see that if we attempt to draw in a representative rectangle that's oriented vertically, it touches the same function on the top and the bottom. This would effectively give us a height of 0 if we use our previous techniques. If we instead draw in a horizontal rectangle, we might be able to find something that works for us. Notice here that the height of this rectangle is going to be given by the right function value minus the left function value. Both of these are functions of y instead of x, and the width of that rectangle is going to be given by delta y. Our region will be bounded by two values, a and b, where a represents the lower limit and b represents the upper limit. This gives us a way to formulate the area between two curves when we have to slice horizontally. Here the area is going to be represented by the integral from a to b of g of y minus f of y dy, where g of y is the function on the right, f of y is the function on the left, and a and b are values that define our interval. Let's take a look at an example that requires us to use horizontal slices. Here we have the functions x equals 2y squared and y equals 2 minus x over 2. X equals 2y squared is already given to us in terms of y. However, our other function, y equals 2 minus x over 2, in order to be able to integrate with respect to y, we're going to have to rearrange that and solve it for x. To do that, we'll subtract 2 from both sides, multiply both sides by 2, and then divide everything by -1. This yields the function x equals -2y plus 4, which gives x as a function of y. Now we can see that the right-hand function is going to be given by the function x equals -2y plus 4, and our left-hand function is going to be given by the function x equals 2y squared. Putting this together, we can see that our area is then going to be the integral from a to b of the right-hand function, -2y plus 4, minus the left-hand function, -2y squared, dy. Now we need to find a and b, which will be our limits of integration. In order to do that, we'll set our two functions equal to each other. This gives us the equation negative 2y plus 4 equals 2y squared, which is quadratic in y. So we get 0 on one side. 0 equals 2y squared plus 2y minus 4. Factoring out a 2, we get 0 equals 2 times y squared plus y minus 2, which factors as 2 times y plus 2 times y minus 1, giving us y equals negative 2 and y equals 1 as our limits of integration. Putting this all together, we see that our area is going to be the integral from negative 2 to 1 of our right-hand function, which is negative 2y plus 4, minus our left-hand function, which is 2y squared dy. Taking antiderivatives, we get that this is negative y squared plus 4y minus 2/3 of y cubed, evaluated from negative 2 to 1. Plugging in 1 yields negative 1 plus 4 minus 2/3. Subtracting what we get when we plug in negative 2, which is negative 4 minus 8 minus 2/3 times negative 8. Simplifying, we get 3 minus 2/3 minus negative 12 plus 16/3. Combining terms with similar denominators, this yields 3 plus 12 minus 2/3 minus 16/3, which gives us 15 minus 6, which means that our area is 9 square units. Let's look at one more example. This one can actually be done using both approaches. If we consider vertical rectangles, then we can see that to the left of the y-axis, our area is going to be given by the integral from negative 1 to 0 of x cubed, our top function, minus x, our bottom function. To the right of the y-axis, our area is going to be given by the integral from 0 to 1 of x, which is now the top function, minus x cubed dx. Taking antiderivatives, we see that this is x to the 4th over 4 minus x squared over 2, evaluated from negative 1 to 0, plus x squared over 2 minus x to the 4th over 4, evaluated from 0 to 1. Plugging in, we get 0 minus 1/4 minus 1/2. Add to that 1/2 minus 1/4 minus 0. Putting this all together, we see that our area is going to be 1/4 plus 1/4, which is 1/2. Drawing in horizontal rectangles, we can see that we need to rewrite both functions so that they are functions of x. Our two functions would then be x equals y and x equals the cube root of y. So our area then is given by two integrals. Below the x-axis, we have the area is the integral from negative 1 to 0 of y, our rightmost function, minus cube root of y dy. Above the x-axis, they switch. We have the integral from 0 to 1 of the cube root of y, which is now on the right, minus y on the left, dy. Taking antiderivatives with respect to y, we get y squared minus 2 minus 3/4 y to the 4/3, evaluated from negative 1 to 0, plus 3/4 of y to the 4/3 minus y squared over 2, evaluated from 0 to 1. Plugging in, we'll get 0 minus 1/2 minus 3/4 plus 3/4 minus 1/2 minus 0. Putting that all together, we get 1/4 plus 1/4, which is 1/2, which is the same value we saw before. Putting it all together, recapping our key ideas. To solve these problems, you're going to need to sketch your graph first. You'll need to find intersection points. And you should probably sketch in 1 or 2 rectangles to determine which method is going to be more effective. If you determine your method is vertical slices, then when f of x is bigger than g of x on the interval a to b, your area is going to be the integral from a to b of f of x minus g of x dx. If instead you determine you need to use horizontal slices, then when f of y is greater than or equal to g of y on the interval c to d, which means that f is going to be to the right of g of y, then our area will be the integral from c to d of f of y minus g of y dy.